I'm Ben Fisch. PhD student at Stanford, but I've been sort of leading the research on Filecoin's mining protocol, proof of replication. So I'll just give a quick 5-minute update on our progress on that. And I also want to preach a certain way of framing why Filecoin mining is so unique. So, of course, there's a large focus on decentralized storage networks, and this is what IPFS is, and you can think of Filecoin as an incentive layer for a decentralized storage network. And there's advantages such as, censorship resistance, persistent availability, all kinds of things that IPFS is focused on. But Filecoin mining actually is really unique in a different way. And I want to focus on that kind of framing. And this is a focus on what the blockchain footprint is. So, of course, you know that the Bitcoin footprint is energy consumption, right? Bitcoin consumes a tremendous amount of energy as a byproduct of maintaining a blockchain ledger. And I don't necessarily back this research from Morgan Stanley, but just to pull something from the web, Bitcoin if Bitcoin were to continue, would be projected to consume a tremendous amount of energy, on the equivalent of a small country. And proof of space is the camp in which Filecoin sits, along with other blockchain protocols. And I want to distinguish what is really unique about Filecoin's proof of space in comparison to others. But in general, proof of space is a reusable form of mining. So it has a greener footprint, like no footprint, right? But what is Filecoin's footprint? Filecoin actually has a positive footprint. Filecoin's mining protocol, as a byproduct, stores real useful data. So proof of replication, which is Filecoin's unique proof of space protocol, is a proof of space, but on useful data. And this is a very unique property of a proof of space that no other proof of space has, that we were able to develop and achieve. And what is the security notion of Filecoin proof of replication? Well, it's something called epsilon rational replication. It's something that we've developed over the course of the year, and it captures a proof of space miner's cost for storing useful data versus junk data. And so in essence, it is a epsilon Nash equilibrium for all the miners in the system to store data, useful data, just literally as a byproduct of mining for the blockchain as they would otherwise. So there's a new research paper, number 1, that I'm going to plug for that you should all check out, which is about proof of replication as a concept, as a proof of space on useful data. It's up on ePrint, which is an archive for cryptography papers. And this introduces a formal security model for how proof of replication should be analyzed and proved secure. So it is the basis for our constructions, but can also give insight into how you might construct other proof of replications and analyze their security. And then there's a second research paper up on tight proofs of space. Tight means that the security gap between the amount of space that honest provers, Filecoin miners need to use, and the best possible Filecoin, mining adversary who's trying to use less space, it's tight if any adversary has to use like 99% of the space that an honest miner would use, okay? And the intuition for why this achieves epsilon rational proof of replication is because no matter what you do, you have to use 99% of the space. So even if you take some adversarial strategy and you're storing some junk data in the process of doing that to help your algorithm work, it doesn't matter what you're doing. You could store real useful data and you would lose at most 1% of the storage. So tight proofs of space and epsilon rational PoReps are very tied together. The PoRep that we actually have is called a zigzag PoRep, which has to do with the topology of the graph that it kind of encodes the data. And so yeah, you should just go check this out on ePrint. Our PoRep has short proofs, fast parallel data extraction, but slow sequential replication, which is for security. Thank you.